Hey Gus, we're rolling.
Sorry. Welcome back. Today we're gonna be having fun with analog inputs. Typically an input, a pin going into a microcontroller, an input is either high or low, 0 or 1, true or false. It's a binary value. It's just, there is voltage on it and there is no voltage on it to whatever logic level that pin is. Usually 3.3 volts, since most micros are 3.3 volts. So when you press a button, let's say that pin, the button shorts that pin to ground, and then that would be low. If you release the button, the pin goes to 3.3 volts through a pull-up resistor, and then that would be high. So now you have true and false. That is a digital input. But that would not work when, let's say, you are measuring temperature or certain values. And this is where we need analog inputs. So those analog inputs have special circuitry inside the microcontroller that takes that voltage level, and usually it's between 0 and 3.3 volts. You take that voltage level, and then that is encoded to a digital value. And let's say if you have an 8-bit analog inputs, that would be from 0 to 255. That's the range we have on a byte. So that's not very accurate. That's why most analog inputs, there will be, let's say, 12, 16 bits, or even more, depending on how accurate you want to be on your measurement, how many steps you can take it through. So now we said the input is 0 to 3.3 volts, but that may not work for your application. This is where there would be a circuit external, and this circuit would scale that incoming voltage. Let's say you're measuring a car battery, that's 0 to 12 volts. So you would take that 12 volts, and there will be a circuit that divides the voltage down like by 4, and then you have a voltage that is reasonable that you can use on the analog input. Now that's beyond what we are covering here. We're just strictly talking about simple analog inputs. I have several examples here. So what I did to show you the analog values so you can visualize them and like get the idea across. We have a fuzz over here, and then I am connecting something. Let's say in this case I have a joystick, and a joystick outputs an analog value depending on where I move the joystick. The output from the joystick is connected to the voltmeter, and I used an analog voltmeter, so it's easy for you to see what's going on. So if you look up at the needle up there, and if I move to the right, to the left, you can see the voltage changing. That's the actual voltage coming out of this joystick, which is internally, it's a potentiometer, which is a name for a variable resistor. So this variable resistor changes resistance depending on the position, which will change the voltage coming out, and you see it on the voltmeter. Now in code, I'm reading over here on the microcontroller, I'm reading the voltage coming in and converting that to a frequency output. So you can actually hear the change. So it's easy for you to get the idea across. Now in your code, you're going to take this analog value and you're going to do something with it. Let's say you have a temperature sensor, and then when temperature is too high, you want to turn on a fan. That's why you would do it in your code. Check read analog input, it's higher than value X, and then that will do something. In this case, I just have a value coming in, and I output this to the speaker. So the speaker is connected to the analog, the PWM output, which I'm just sweeping through frequencies depending on the analog coming in. So this is an example. Nice. Now, I want to show you an example of a sensor. So in this case, you just have a variable resistor, but I want to show you a typical sensor. So this is, for example, is a light sensor, which is basically, it's a resistor that changes value depending on how much light it's getting. So let's try it. Darker, brighter. And you can see the output changing on that on the voltmeter. Yeah, analog voltmeters are awesome for an application like this. You know, and probably you do not have an analog voltmeter anymore, but I love this analog voltmeter. I use it in a lot of applications. This is another example. So this is pretty sweet. So let's say you have multiple buttons, but you don't have that many digital pins, or you just don't want to wire, let's say in this case we have 5 buttons. So is there a way that you can read those 5 buttons without having 5 wires, like 1 to each button? Yes. Each one of these buttons is connected to a resistor, and the resistors are up around these buttons, and each resistor has a different value. So when each button pressed will connect a different resistor on the wire, causing a different voltage to output. And then you can measure these voltages, and you can determine through the voltages that one of the buttons is pressed. And well, we can see that as well. So let's turn the speakers on. So press this button. That's a really high voltage, high pitch. Press this button. It's a lower voltage. This one is a little bit higher, a little bit higher. And that's how you can get multiple buttons connected on using the same wire. Different example over here. I also have a moisture sensor, and this is extremely basic. This all it is really is a bunch of traces, and they are alternating. One trace is like every other trace is connected to a resistor, and every other trace is going to ground. And then when moisture, something conductive, goes between those traces, that changes the resistance of the overall resistance of the circuit, which changes the voltage. For example, my finger is that's not moisture, but it's conductive. So I can touch the circuit. That also changes it. Now, if I wet my finger, it's a lot higher. It's actually now it's wet. You can see it doesn't go back. Dry it up, and then it goes back to the original frequency. So that's a moisture sensor. And this is a pretty sweet example. So this over here is basically a matrix of buttons, a lot of buttons. And this is the exact same one, but this one is done through a matrix. We had another tech talk where we talked about matrix and how you would have like columns and rows and how you would scan through them to reduce the amount of pins you need. So over here, there are many buttons. There are fewer pins, so this would be, they are connected like columns and rows, and this is how you get fewer pins. But then you can reduce this to just one pin, one analog pin, and that's what we have over here. Now, the disadvantage of this one is that you have to scan one row at once, meaning you cannot press 2 buttons at the same time in a row. You can do it in a column, where on this one, you cannot press 2 buttons at once. You can only press 1 button at once and detect that button. If you have them connected individually, then all buttons would work. So let's say in this application, it's okay to have multiple buttons. Let's turn the audio on. So it looks like the more I go this way, the lower the voltage is. You can see this is really low. Higher, higher, higher. So you're okay just detecting 1 button at once. 1 wire would work using an analog input. And like I said earlier on this one, each one has a resistor. These are the resistors on the back, and each one of these resistors is connected to one of the button. Different resistor value, different voltage on the output. This is it for analog input. I hope you enjoyed this video. I would invite you to take a look at the code. It makes things a lot easier, and you would see how in .NET, when you read the analog value, you can just read the ratio, because that's just easier. So when I'm scanning from 0 to 3.3 volts, instead of reading a voltage, I get a value between 0 and 1. So 3.3 volt will be 1, 0 will be 0. Why is this nice? Because now I'm getting a ratio from the lowest value to the highest value. So for example, when I want to generate frequency, and let's say the frequency I want to generate is between 1000 hertz to 5000 hertz, I just take that 0. Whatever, that's between 0 and 1, the analog value coming in, I multiply that by 5000, and I automatically now scale that value to 0 to 5,000. And this is how I can easily scale that value to whatever it is. Let's say the voltage coming in is 0 to 12 volts, like you have on your battery, and you have a circuit that's scaling it to 3.3 volts. All you have to do is take that ratio value you're reading that's between 0 and 1, multiply that by 12, boom, you have the actual value you are reading from the battery. I hope this was educational for you, and go ahead, have fun, analog inputs. See you next week.